Bună ziua! O să începem cursul de Practical Machine Learning. Cursul voi face în limba engleză. Aș vrea întâi să mă asigur că mă puteți vedea și auzi. Pentru comunicare vom folosi chat-ul de pe Facebook, adică puteți scrie în chat. Eu o să pun întrebări. O să aștept răspunsurile tot așa în chat. Știu că e un pic de delay, dar cred că lucrurile vor merge ok. Bun, în regulă. Deci văd că lumea deja s-a conectat și primesc răspunsuri că mă auziți. Deci numele meu este Radu Ionescu. Cu o parte din voi probabil că am mai făcut cursuri, dacă ați terminat licența în cadrul facultății. Dacă nu, ne vom cunoaște cât se poate prin intermediul virtual în cadrul acestui curs. În principal vom studia metode de... am început în română. We will discuss about machine learning methods in these lectures. And mostly about how to apply them in practical applications. So this is why the course is called Practical Machine Learning. So my name is Radu Ionescu, and I will be teaching this lecture during the first semester, and the discussion will continue on the second semester with advanced machine learning, where you will also address more of the theoretical concepts in machine learning. So this domain is a subdomain of artificial intelligence, and recently it became, I think, the most important subdomain in artificial intelligence. So it comprises different machine learning methods that can be applied in different domains. So it is connected with natural language processing, computer vision, and other domains, signal processing, and so on. We will also discuss about some applications in natural language processing and computer vision. And since this is a practical course, you will also have to do some projects in these fields. So we will discuss immediately about the grading system and the projects, but first I want to let you know about the people that are going to teach. So at least for I already introduced myself. So for the labs, you can work with 3 teaching assistants, Antonio, Michael, and Marius. You have their email address on this slide, so you can contact them directly. So essentially, I think that if I remember correctly, Antonio and Michael, they split the AI groups. They have each of them has 2 groups from the AI, 2 subgroups from the AI group, and Marius has the data science group and the natural language processing group. So either way, there are 6 semi-groups, and 2 of them are allocated to each teaching assistant. So the lab is once every 2 weeks. So one group, if you belong to one group, you will have to do the lab once every 2 weeks. So there will be a total of 7 labs. So first, the people that had the bachelor in our department, we assume that they already know Python, but since we already have people from different places like Polytechnica, of Bucharest and so on. We will also have an introduction laboratory to Python. So this will be the first lab for you. Okay, so about the grading system, you will have to prepare 2 projects. So in this lecture we will discuss about different learning paradigms. Actually, the most important ones are supervised learning and unsupervised learning. So I will present today what are these paradigms, and you will have to create a project for each kind of paradigm. So different models belong to these 2 paradigms. So first we will discuss about supervised learning, and then we will also discuss about unsupervised learning. So the lectures are kind of divided in half. So you have to prepare a project for the first half and another project for the second half. So since actually these are not equally in half, so we have about 9 lectures, or actually this one is a more generic lecture, then we will have 8 lectures for for supervised learning, and we will have 5 lectures for unsupervised learning. So the proportion is not really 50-50, so this is also reflected in the grade. So your projects will be individual, and each project will consist on employing some machine learning methods. Some of them have been presented over the previous slide, and we will discuss, we'll try to cover as many methods as we can in this lecture, but of course you can also use different methods for your projects. So the first project regarding the supervised task will be to participate in a Kaggle challenge. So we will propose a competition on Kaggle. Preferably by the end of October, we hope to launch it, and you will have to participate in this competition, and we will discuss about the grading system regarding the first project immediately on the next slide. And for the second project, since unsupervised approaches are not really that easy to evaluate, we are going to actually use individual projects in which you have to compare 2 unsupervised approaches. And for this project, every student has to choose 2 methods to compare, and a data set to apply the methods on. So since there are many data sets out there, we do not allow overlap on the data set. So each student has to propose his own data set and use it for himself. Okay, and of course we expect you to propose the methods and the data sets for the second projects beforehand, so at least 2 weeks before the deadline. So you need to tell us the chosen methods and the data set, and we have to approve it before you can start working on the project. This is to ensure that there is no overlap with other students regarding the data sets. Okay, so for the first project, we will set up a deadline in week 10. So this is actually, I think, 1 week after the last lecture on the supervised learning topic. Okay, and then the second project will have to be presented on the day of the exam. So you will be evaluated only based on these projects, and there will be no paper exam, so only the project evaluation. So we will make a weighted average, like 60% and 40%, but the average has to be greater than 5. And the project in both cases will consist in implementation in Python, a PDF report that includes the description of the dataset. This is required for the second project. For the first project, all of you will use the same dataset, so there is nothing else to discuss about the dataset. And you will also have to include a description of the implemented machine learning methods, figures and tables with results and comments on the results, and of course a conclusion. So now I figured out that I didn't include the slide for the first project. So I will include the slide. I'll try to include it right now. So yeah, we will have also extra points during lectures and labs. So we will give for each answered question or solved exercise, we will give 0.2 points, and we will have a maximum of 0.4 points per lecture for each student. So this means that if you answer 2 questions, you will not get points for the third question. So this is to encourage every student to participate and to try to solve the exercises and to answer the questions. So and in the end, we will probably give up to 1 or 2 points in total added to the final grade. So sorry, I'll have to go and steal the slide from a different lecture. Yeah, it's this one. So I just forgot to include this slide. So okay, so there will be a first project that consists of implementing some machine learning method or methods for a Kaggle challenge, which will be announced. So the grades in this challenge will be proportional to your model's accuracy. So based on the total number of people that are subscribed, so we will try to set up the threshold of 120 here. So yeah, I have to increase this a little bit because here it's a bit so these are in the other course I had less students, so I could go with shorter thresholds, but they should be a little higher. So let's see if this works. No, this is not enough, so we have to go maybe like 120 here, 21, 50, 51, 80. Yeah, this works. 80, 100, and 101. Yeah, so this will be the ranking and the grading system. Okay, so now we have this slide also in. So this is for the first project, okay, that will be proposed in by the end of October. Sorry, this is not a valid point here. Okay, great. So we also have the grades for the first project. So I think I covered, yeah, and there is also this collaboration policy. So we had some trouble with last year students. They didn't really understand what this means. So we want you to work on individual projects, and we want you to not borrow code with copy paste from online web sources or among each other. So this is not allowed, not even. So perhaps maybe to make it more clear for you, I should where was that? Oh, sorry, I open this and I should borrow this here. Sorry, so this is from the other lecture. Yeah, and this is also an important slide that I forgot to add. Okay, and I wanted to write here is not permitted. Okay, now it should be very clear. Yeah, so and also, so the main idea is we want you to write your own code and to be able to implement the presented concepts yourself. So we will check the code and make sure that you respect these constraints. Okay, this is much better. So yeah, if you have any questions about the organization, the grading system, and so on, please ask the questions. You can of course also write an email afterwards, but yeah, so we already have some questions. Yeah, we will. So you will present the project. So first, there will be a deadline. So we have to submit the projects by email. So we have an official email. I think the email is practical. Yeah, this is the email address. So you will submit the projects on this email address. Probably I should put it maybe here. So this I should remove. Yeah, so you will submit after the deadline of the competition, you will submit the project to this email address, and then we will set up a date for a presentation. So you will have like 10 or 15 minutes to present the project. Yeah, so for the presentation there will be we will also look for these items here that you have to present. So also for the Kaggle competition, the documentation and the presentation can account for 2 points. So these are the starting grades. So for example, if you do not include the points mentioned in the presentation, you can get a grade. Your grade can go down to 8, let's say, if you're in top 20. So there will be a maximum of 2 points that can be subtracted from this grade. So we do not want to do this, so preferably you try to follow the guidelines and include everything that you are told to include. Okay, so this is about the presentation. Yeah, so we will propose the competition for you. So yeah, it will be a custom competition only for you, no external participants. Yeah, you don't need to make a presentation, you need to make a PDF report. Yeah, so you exactly, so we can also deduce a maximum of 2 points for the presentation for the first project. So this is to encourage you to make the report, and yeah. Okay, so yeah, I think we have all the required slides here, so it's all good. Yeah, so before going on, let us see if there are still any questions. Yeah, you will not need computing power because the data set, so yeah, will not be that large. So we will make sure that that the data set is manageable. Okay, so you will not use I don't know, tens of thousands of data points and so on. So it will be something that that you can train I don't know, on a laptop or something like that. So don't worry about not having computational resources, but yeah, anyway, I think you can also use Kaggle for this. They have some platform where you can run, or you can use, as your friend says, Google Colab and so on. Yeah, so don't worry about large data sets, and you have to about training very deep models and so on. So actually we're not really concerned about training deep models, so we will cover some of this, but essentially this will be the topic of next year. So still we will use not so large data sets for you to try. Okay. Yeah, transfer learning is possible. I also saw this question. So we will when we will launch the competition, we will make more clarifications then, but yeah, I think you get the general idea about the evaluation and so on. Yeah, so all the videos will remain on my YouTube channel, and I think I already gave the link for the slides for the PPT. So the website is practical. Yeah, I don't know it by heart. So if you go on my website, yeah, so it's practical -ml fmi github.io/ml. So I think I already gave you this link. Yeah, I already updated the slides, so I will also update them on the website. So yeah, I will put the slides in the same, perhaps before or after the presentation, but in the same week with the presentation, I will also update the slides on the website. So yes, you will have, I actually prefer to put the slides after the presentation, because during the presentation, if I see some mistakes and correct them, I'll make sure that that the slides are updated on the website. Okay, sorry, I forgot to check if there are still any other questions. Okay, so I hope I answered all your questions, so I'm moving on because I don't want to lose too much time on this. Okay, so artificial intelligence is about building systems able to reach human level intelligence. And one way this is defined is through the well-known Turing test. So Alan Turing, the father of computer science, proposed a test to decide if a computer has human level intelligence or not. So there is a human here denoted by C that is speaking through some occluded wall with a subject, and he doesn't know if this subject is is a machine or another human. So essentially he can interact through I don't know, written chat or something like that with these this subject, and in the end, if the machine tricks the human judge that it is a human, that he is speaking with another human, it means it passes the Turing test. So this is a very challenging test, and in with limited time period, there are systems that can pass it. So yeah, if you can interact within, let's say, a window of 10 minutes or 15 minutes, it is hard for the human to figure out. But if you give enough time, I think there is currently there is no AI system that can actually trick humans into thinking. So there are really aspects that are very tricky here. So for example, if I can ask the computer, for example, or the guy that I'm speaking with, to add up two numbers, and I can actually decide that he is a human or a computer by seeing how long it took him to answer the question. So of course a computer can make the computation fast and provide the answer straight away. So this could be a trick to figure out if it's about a computer or not. And the computer will have to program in especially some delay if we want to trick the human to these kind of questions. Yeah, so this is an open area of research, and it discusses more about generic AI, and we will come back to this a bit later. But either way, even if we don't pass the Turing test, I think we're taking steps in this direction. So there are many things that computer can do. And yeah, Alan Turing posed the question in 1950 that can a computer convince a human that it is not a computer but a real person? So this was the Turing test. And now we have to actually solve these CAPTCHA systems so that we can convince a computer that we are a real person and not an actual computer. So it means that we have bots that can trick systems into giving up information and so on. Yeah, so this is more intended as a joke, but with some serious question behind. Okay, so we discussed more about artificial intelligence. So what is machine learning? So one approach to reach human level intelligence is to try to imitate the way humans learn, and machine learning is about imitating how humans learn. So this is one possible way. So instead of trying to program the human level intelligence directly into a system, we're trying to learn as humans do and hope that the system will reach human level intelligence. So this is the main approach in machine learning. So we can say that formally is the scientific study of algorithms and models that computer systems use to learn from observations, like from data, without being explicitly programmed. So here actually learning can refer to recognizing complex patterns in data and making intelligent decisions based on the data observations. So there is the last part, without being explicitly programmed, means that we are going to a new paradigm. So in classic programming, you have some input data and some program, and the computer runs the program on the input data and you get some output. So for example, you have, I don't know, you have some numbers A and B, and you want to add them up. So you have a function, a program that computes the addition, and you get the output, the sum of the two numbers. So in machine learning, you don't have the program, but you have the data and the output. So for example, you have examples, instantiations of A and B, like, I don't know, 3 and 5, and you have the corresponding output 8. And you have, I don't know, different examples, like, I don't know, 4 plus 8, and the output 12, and so on. So you have a bunch of these examples, and you want to make the computer to learn this association between input and output. So the computer actually, from the learning process, it generates a program that will map your input to your output. So this is the main concept and the main change of paradigm from classic programming to machine learning. Okay, so we discussed about well-posed machine learning problems. So now we know the paradigm shift, and we're thinking, okay, so we have this new tool that can output programs, or can learn from data. What kind of problems I can approach with machine learning? So we also have a definition for what means a well-posed machine learning problem. So I like to use the definition of Tom Mitchell that refers to three key components. So we have an experience E, which is the data that we have available. So the examples that I gave you before with 3 and 5 and the output 8, 4 and 8, the output 12, and so on. You have some class of tasks. So in this case, you want to so the task is very simple. Yeah, you want to learn the addition, but in general, you can learn to classify objects and images and so on. So there are different tasks here, and you have a performance measure. So since the task is not that trivial, like the sum of two numbers, the output can also be wrong sometimes. So you have a performance measure that gives you an indication of how many times your program produces the correct output and how many times it produces the wrong output. So you have also the performance measure. So now if we have these three components, so we can say that a computer program learns from some experience E if its performance measure improves over time along with the experience. So since we imply here a performance measure, we discuss about a degree of accuracy, and this can be measured in different ways. We will discuss more about this in the next lectures. Okay, so probably the first example of well-posed machine learning problem is the one proposed by or addressed by Arthur Samuel in 1959. So he wrote a program to play checkers that was based on these concepts defined by Tom Mitchell. So he devised the program to play around 10,000 games against itself. And the program was designed to find good and bad positions on the board from the current state. And it was based on the probability of winning or losing from the respective positions. So the games that the program played represents the experience. The goal that you want to solve is to learn a model that plays checkers. So this is the task, and yeah, the performance in the end is measured if the program wins or loses at checkers. Okay, so this is a particular example of machine learning. So in this example, if we particularize to a certain task, we're usually discussing about weak AI. So we make this distinction of a strong AI and weak AI. So strong or generic AI refers to a model that has human level intelligence, more like in the Turing test, and is able to solve a lot of problems. So for example, in order to be able to communicate properly with the humans, with a human, you need to solve a lot of tasks. So you need to understand what he says. You need to do, I don't know, disambiguation. You need to understand named entities like places, like people, and so on. You need to solve co-references like the system is talking sorry, you're saying something about Ben, and then you ask what is the age of Ben, and what is his age. So the computer has to infer that his refers to Ben. So there are a lot of problems that require solving in order to achieve generic AI intelligence. And this is the example of Turing test was initially posed only regarding with respect to language, but now we also have we can discuss about a visual Turing test where you also have to the system also has to understand images and videos and so on, and this can be further extended to speech and so on. So it becomes more and more difficult. So yeah, the approach that if you want to try to solve every task and put it in a single system, it will not work like that. You have to come up with something else. So at the moment, we do not have a system that is built with a generic AI, but people are working on this research topic. So most of the problems that we're going to present next refer to weak AI or narrow AI, which is focused to a specific task. And here we can define the task. We can use easily add training data and learn a model on this task. Okay, so when do you use machine learning? So for example, as I stated before, there is a paradigm shift. So if you have data and a program that you can write for your data, like a sequential program, so you take these explicit steps, explicit rules, and obtain the output, then you should do it like that. So it's not the case to use machine learning. But if that's hard or impossible to do, for example, if you want to recognize objects in images, I think it's very hard to write a program to do that and to program every rule inside it, because there are many exceptions that you can probably not even think of, and in the end you will probably not get the expected results. So yeah, instead of trying to write the program, then you can try to employ machine learning. So in this kind of problems, of course, we use it is better to use machine learning than standard, let's say standard programming. So examples are face detection, speech recognition, stock price prediction, object recognition, and so on. So we will discuss about some of these examples, but we will also try to define the paradigms that they fit into. Yeah, so it's that the main idea in machine learning is that okay, you cannot express your problem or your solution programmatically, but you have some data on it. So for example, for object recognition in images, we can collect images from the internet, and we can also have labels for them. So we can, as humans, we can label the images like with this is a car, this is a person, and so on. And also there is a pattern in this data. So for example, if we think of cars, there you will find a common pattern of or common patterns on how they look. So for example, they have four wheels, right? They have windows, they have a steering wheel, they have I don't know, pedals, they have lights in front, usually white lights in front, red lights on the back. Yeah, they are made of metal. um, they have like a squared shape and so on. So there is a common pattern that you can see on all the cars, and you can easily identify that this is a car and this is something else. So if you can observe this type of patterns in the data, then probably it is a task for machine learning. Of course, there are cases where it is hard to see these patterns. So if you're working with some abstract data, you cannot identify these patterns yourselves, but anyway, it is still possible to try out machine learning and see what is the output. And people manage to successfully solve a lot of tasks that were previously thought to be impossible for machine learning. Okay, so now going to back to the definition of machine learning. There are different ways that express the same concept. So there is a definition from Arthur Samuel that says that machine learning gives computers the ability to learn without being explicitly programmed. So essentially the one that I started from. There is also a definition from Kevin Murphy that refers to automatically detecting patterns in data, so what I discussed before. And there is also the definition from Tom Mitchell that I presented. So yeah, these guys started pretty early in this field in the 1950s and the 1960s, and yeah, in that time they thought that AI can be solved easily. So the first proposal in this topic was made by some group of researchers during a summer research project on artificial intelligence proposed by mainly John McCarthy. So in their proposal, they said that AI can be solved like in a 2 months project if they gather around 10 researchers in the field. So this was proposed in the summer of 1956. Yeah, and they proposed actually they thought that they can solve the artificial intelligence problem. So actually the problem of building a machine with human level intelligence just by describing every aspect of learning programmatically. So yeah, they thought if they can describe this, they can also build a machine to simulate this program. So yeah, they will try to, in this project, they try to make an attempt to solve this problem, and their statement was that they can make a significant advance yeah, if they use a carefully selected group of scientists for a summer. So yeah, the main idea was that they thought this was very easy to do, but yeah, it turned out not even they didn't solve it in 2 months, but it's still an active area of research, and people are still trying to build strong AI. So they underestimated the task, with more than 60 years of research. So they thought they can solve it in 2 months, and we are 60 years past that time, and we still didn't solve it. So it was a huge underestimation. So anyway, in the 1960s and 80s, so going back to the history, so this is how it started, with a small project that they thought they can solve in summer. It turned out to be very hard, and people tried to work in this area. There were even voices that said that AI can never work because it's too complex. And there were some examples, like some report of Minsky and Papert, that was made on the first model of artificial neuron, the perceptron of Rosenblatt, saying that it was a very simple and stupid model. It cannot learn even the XOR function, and it will never work. So essentially, they kind of sealed the domain for a couple of years. So the advances were scattered in this time. But in the 1980s, so in about 1986, people started to use to use neural networks after the discovery, or the let's say, so the algorithm was, I think, from the 1980s, a bit earlier, but it was introduced to the large public in 1986 by Hinton and his group. So people started using and training neural networks, which combine more of these artificial neurons, and they started to obtain some interesting results. But still, the domain didn't find so many applications. So people turned to a different kind of approach, kernel methods, which dominated the field in the 2000s. And people started to use these methods because they were more stable. So if you train a kernel method twice, you should obtain always the same solution, while in neural networks, the learning process involves some stochastic optimization, and you will always get a different result. Okay, so the problem with both these simple neural networks and kernel methods is their instability. Not instability. The poor results. So they don't have so many applications. They have strong results in specific applications, but there are many real-world problems that cannot be solved with this method. So in 2010, the neural network approach started to become in the center of attention, with the idea of using deeper models, so neural architectures that have a deeper structure. So basically, with the introduction of the deep learning concepts, people started using neural networks again, and along with the development of the technology and the hardware, we had more computational power. People started to use GPUs to train deep neural networks, and also more and more data became available, and so the accuracy started to increase. So of course, when you have more training data, you also need more computational power to train your models. So all these played a very important role in where AI is today and where deep learning is today. So now there is a lot of interest from the industry on machine learning because of so many interesting applications. Okay, so just to make a summary of machine learning. So yeah, there are many algorithms out there that are introduced so far, and researchers publish new algorithms every year. So all this can be summarized, can be oversimplified into the following statement. So in machine learning, we want to learn a mapping function f from an input x to an output y. So this is the generic formulation. So you want to learn the function that maps the input x to the output y. And now you can particularize this generic formulation to different instances. So for example, you can use machine learning to solve the problem of email spam. So you want to classify emails into spam or not spam. Then you have the input X, the emails, you have the labels. So this is spam, this is not spam. And you use this data to learn a mapping function to assign the correct label to each email. Yeah, so this is now, for example, if you have an email inbox, so if you use email and you have a junk or spam folder, the emails are sorted out using machine learning. So probably you already observed that the system is not perfect. There are some cases in which emails that are not spam are added into your spam folder. It happens sometimes. And also there is some spam that goes into your inbox and it's actually spam you don't want to see there. So we always see these cases, but most of the times the classifier works fine. So this is one of the many applications of machine learning that you probably use in a day-to-day, perhaps even without noticing. Yeah, and we will give more examples during the lectures today. Okay, so we have this input x and output y. So mainly x can be seen as vectors in some Euclidean space. So r to the power of n, where n is the size of the vectors. And the output can be continuous value if you want to estimate, for example, I don't know, the value of stock prices, or some hard label like spam or not spam if you want to classify instances into classes. Okay, so we have this target function f that is unknown to us, so we want to learn it. We want to identify this function. How we do this is by having some data at our disposal. So we have some examples. So x1 is from this set x, and y is the corresponding label from the set capital Y. So okay, so we have this data, and first we have to make some hypothesis about the model. So we will learn about different models in our lectures and discuss about different hypothesis classes. So one of the most simple models is to assume that this function is a linear function. So for example, for the spam not spam classification task, we can assume that the labels are positive and negative. So let's say 1 for spam and -1 for not spam. So on top of the linear function, which is just the multiplication of some vector of weights, transposed with some input x from the data set. So x here takes place instead of x1, x2, and so on. We apply the sine function on top of the linear function, and we obtain the corresponding labels +1 and -1. So yeah, so this is the model class, means that we are using a linear function that has this form, and we have a particular instance, a particular model, when we have also defined this vector of weights. So now W, if we refer to the hypothesis class, W can have any value. If we particularize the model, if we train the model, we obtain a certain weight vector, and yeah, the learning process actually in this case would be to find the vector of weights W that gives us the function G that that best approximates the function F. Yeah, so this is done usually with initializing the weights randomly, and then we apply some optimization algorithm to minimize some error function or some performance measure. Yeah, so we will discuss more about this in detail in the next lectures, but this is just a brief introduction to what machine learning means. So in the end, every machine learning algorithm has three components. So the model class, or the data representation. Yeah, this can be either done independently. So we can, for example, figure out how to represent the images as some vectors in a Euclidean space. So this is an handcrafted or engineered part. And then we apply some model on this representation, on the obtained representation. And this can also be done in an end-to-end fashion using deep learning, but we will discuss about deep learning next year in more detail. We will also make some references in the practical machine learning class. Okay, so this is the first component. The second component is the evaluation or the objective function. So regarding the evaluation, we are going to discuss more in the next lecture about different evaluation functions and so on. And also an important part is the optimization procedure. And yeah, we will start with models that don't really require any optimization, like nearest neighbor models. And we will also gradually introduce neural networks and discuss about gradient descent, which is the algorithm used to train neural networks. So in this field, you actually need a lot of components from connected domains. So first of all, from computer science, you will use algorithms, data structures, and so on. So for example, if you want to optimize nearest neighbors, one idea is to use KD trees. Yeah, so I just remembered now a short deviation. So for the people that had the bachelor at our university, so they were enrolled in our bachelor program, have seen some of these slides, I think. So here in the master program, we will have to reuse some information, because there are people that coming from other places and they need to reach the same level. But also we will discuss in more detail some of the aspects. So we will also introduce new algorithms. So about half of the slides are completely new. So because now we have 14 slides, and in the bachelor we had only 7. so only 7 lectures, but even for those we will have different new details about the presented models. Okay, so I think you took a picture of this slide, so I'm not going to discuss too much about it. So yeah, we use concepts from biology and neuroscience, so here you don't have to worry too much. I'm just going to explain the links and that's it. But I don't know, regarding computer science, statistics, and applied mathematics, that's really things that you need to know. So, and we will not cover in this lecture because it's not enough time. So at least the basic concepts on linear algebra, derivatives, what means a local minimum, and so on, we will still present the main concept, but will not go into so much details. Yeah, so that's that. Okay, so about the learning paradigms. Yeah, so there are the standard learning paradigms like supervised learning and unsupervised learning. And sorry, so let me just make a quick break and see if there are any questions here. Okay, so there is one question, relevant question, if you're going to learn about time series. Yeah, so we will cover some about, so probably this is more a regression problem, and we will cover the regression task and also during the lab. I'm not sure if the topic during the lab will be about actually time series, but yeah, we will cover this part. And unfortunately, about the more modern approaches for time series like recurrent neural networks will not be discussed in the practical machine learning lectures. They will be discussed in the second year of your master's in the deep learning course. They will have a special lecture only for recurrent neural networks. Okay, so yes, no big questions to answer here. So going on forward, yeah. So the third learning paradigm is semi-supervised learning. And we also have reinforcement learning. So all these are considered standard learning paradigms. And there are people working in only these specific domains. And we also have non-standard like active learning, which is actually becoming more and more a hot topic in the field, and people started to use more and more active learning and also transfer learning. So they are still not considered standard, but they are given a lot of attention. Okay, so we will try to give examples of problems for these paradigms in the remaining time. There isn't so much time left. But yeah, I'm trying to give you examples to understand what they mean, and try to define them. So yeah, in supervised learning we have a set of labeled training examples. So the first example is object recognition in images. So in object recognition, we have some images with different objects, and we want to have the labels with the corresponding objects. So the input X are the images, and the label Y are the corresponding labels, and you want to learn this mapping from image to label. Another example that is one of the first success stories of AI applied in a practical application is handwritten digit recognition. So this problem was posed by the US Post Office, and the project was solved by a team from AT&T Labs, which was formed by Jan LeCun and Joshua Benjo. And they proposed a solution based on neural networks. So they gathered a large data set of around 60,000 images, and the images were 28 by 28 pixels, and they had people write down letters and collected them and annotated them, and they then trained the model, and the model in the end was used to automatically sort the mail in the US postal office according to the zip code. So there was a machine that was reading the zip code and sorting the mail based on the area code. Yeah, so essentially they one idea would be, for example, to represent the images as a vector. So we transform the images into a vector, and then we train a linear classifier on top of this. So for this simple example, you can actually apply this approach to transform the images into a vector directly without trying to extract any feature or trying to do something more complicated to obtain a vectorial representation, and you can still get an accuracy of around 95% or something like that with a linear model. But this is a simple problem. If you go to more complex images, the task will be significantly more difficult. Yeah, and these are some examples that show you that the images are not so easy, and even for humans are hard to recognize in some cases. I think this is a set of the most difficult images in the data set, and you can see that, for example, these two here, so these are listed in order, so these are 0, 1, 2, and so on. This one looks really like a 7. Yeah, and there are different writings that are really difficult. So this could also look like a 9, that it's not finished here, and less to a 5, and so on. And this 9 looks like a 4. So in some cases it's really hard even for humans to figure it out. But anyway, they managed to solve this problem with an error of 0.23%. So this means that in 10,000 images, in 10,000 digits, the error is 23. So they get 9,977 correct, and only 23 images wrong. So it's a pretty high accuracy rate. So I think, I'm not sure if these are, yeah, so these are perhaps not exactly this model, but from a model that is very accurate, and actually these are the images for which the model gave the wrong labels from the total of 10,000. So yeah, this is a pretty impressive and successful application of machine learning in the field, and this was done in the 90s. And another successful application that is from a couple of years ago is face detection. So you can see that in this application, the idea is to try to detect faces of people in images. So this I don't know, has application to photograph to cameras, For example, to be able to focus on the faces of people, or I don't know, if you want to have systems like authentication systems, you based on face recognition, you first need to detect the face. So there are many applications of face detection. And yeah, we have also a GIF here with kind of an ideal face detector. So actually the bounding box that the model is supposed to provide, it's actually attached to the face of this guy, so it's more intended as a joke, but yeah, that would be the ideal face detector. Okay, so yeah, this I like this example of problem because it's not really straightforward to see how to model it. So we have uh, the problem that we have is we want to learn a mapping from X to Y. So what is X and what is Y? So in this case, we can model the problem as a classification problem. So we have the X will be some image that represents a face or not, and we have the labels +1 for face and -1 for not face. So the idea is to use this sliding window algorithm. So we have a window that we slide on top of the entire image, and in each location the window can contain a face or not. So we apply our model. Let's say the model is a function g, so we apply it on top of this image and we get an output. So we apply the model on every window, and when we get a positive response, then we have detected the face. Yeah, so the original face detection problem is thus transformed into a classification problem that we can address with machine learning. So in order to detect faces, we need to collect a set of images with people with faces, and here we want to add a lot of variation. So for example, we need to use people with different age, different gender, and different illumination conditions and different poses, so that we can identify people. But here, importantly, one important aspect is not to one variation that we do not want to include is to have translated faces. Yeah, so why do you think this is important? This is a question that I would like you to answer. Okay, so I'll wait for the answer here, and go back to the slide a bit so you can look over it. So we have a set of people with faces faces of people with positive labels, and also we have a set of images that do not contain full faces. So yeah, there are two questions for you. First is, why do we want to exclude translations? And the second question is, why do we need a larger set of images that do not contain full faces? I mean, so for example, if we have I don't know, a set of 5,000 images with faces, why do we need a much larger set of images without faces? So do you have any intuition about these questions? Please state an answer. Okay, so I see some intuitive answers here, but yeah, so that's correct. You need but why the question is why we don't want to have translations. Yeah, I see a good answer. I'm not sure if this answer is from somebody that's subscribed in the lecture. So yeah, the correct answer would be yeah, I also see a good answer from Andrea. So the main idea with the translation, so okay, so this question is answered, and I will clarify it for you. And I'm also looking for an answer regarding the size of the non-face dataset. Why does it need to be larger? Okay, so going back to the problem that we want to address, face detection. Yeah, so we want to detect the face when the window is on top of the face. So imagine that we slide this window in every possible location. So if we go slightly move the window here, then we will our algorithm will give us a positive label if we add translation to the training data. So we slightly translate the faces, we will get many detections over the same face, and we don't want this. We want a single detection. So this is why it is important not to have translation. Okay, so I'm looking for the second question. Why do we need a larger set of non-face images? I think this question is a bit maybe a bit harder, but I'm still going to wait for a minute for a good answer. Yeah, so it's clear that you need non-face images. My question is why the number of non-face images would need to be larger? To eliminate false positives. Yeah, that's kind of, let's accept that as a good answer. So okay, so we have our answers here. Okay, so yeah, why do we need more images with non-faces? So usually the machine learning models also learn the distribution of your data. So if you used a balanced data set with let's say 5,000 images of faces and 5,000 images of non-faces, when you apply it on the image, the probability of saying yes or no is around so the learned distribution is like 50%. So it will expect to see around so if you sample a lot of windows from this image, the model will expect that half of them will be with faces. So probably it will also activate or give a positive label even if the image is not really centered on the face. But if it sees something like a face, it will say that it is a face. So yeah, you kind of want to try to your training data has to be to model the real data. So when you build your data set, you usually expect that in most of the windows you will not get faces of people. So then you want to train to learn this bias in your model. So this is why the non-face set of images has to be larger, as stated here. Okay, so yeah, we will also discuss about this bias distribution in training data in our future lectures. So yeah, I can give you another example of supervised learning and spam detection. So you get emails with spam and not spam, and you want to classify them accordingly. So in this case, for example, we can model, the easiest way to model the problem is to use a representation with a vector of word frequencies. So actually you get your data set, you collect a vocabulary of all the words, and then you represent each email as a histogram with word frequencies. So yeah, you assume that the words from the vocabulary are in a specific order, and then for example on a certain position I corresponds to a certain word. So all the documents will be represented as frequencies of these words. Okay, so one example, so imagine that in the vocabulary we have these words like free, money, amount, and so on. So for example, in some spam email you would expect the frequency for words like free and money and so on will be greater than in normal emails. So these are probably rarely occurring in normal emails. So once you build this type of representation, you just need to learn, for example, a linear model on top of these counts to figure out if the email is spam or not. Okay, so you can also try to use the entire vocabulary, and of course you can also try to eliminate some of the words. So for example, words like the, of, at, in, and so on will likely occur more often in all emails. You'll get a large frequency count, and it might actually bring some noisy information to your model. So you might think that, okay, just let's try to keep some subset of words that are maybe more representative for spam. Yeah, so all about these modeling aspects and about how to assign the corresponding weights, and perhaps even question if the linear combination is the best model or not. We will discuss in the future lectures, but this is just yet another application of supervised learning. So the first, up until now we discussed more about classification tasks, and we can also apply supervised learning in regression. So one application would be to time series data like stock prices. So you have the stock prices until the current date, and you want to estimate the stock price at the future date. So for example, in I don't know, a few days or so on. So this is usually regarded as a regression task since the output is continuous. So actually you want to predict the actual stock price. So this can be a real value. Okay, another example will be to predict the difficulty of images, and this can be used as a task in different many other machine learning algorithm as an extra input. So yeah, you get some images, you can sort them by difficulty, let's say by, I don't know, by the number of objects, and then you can try to predict the difficulty or the number of objects in the image. So this is a regression task. And by the way, you can use this data set, so it's actually put together by our group, and you can use it for the second project in your for your evaluation. Okay, so yeah, to summarize the supervised learning problems, we have two canonical forms: the classification problem, in which you have data points from some Euclidean space, and you want to separate them by according to their class. And regression problems, where you also have some data points. So here in this example, let's say that the data points are represented on this axis, and you have the label represented on the other axis, and you want to model to find a model that represents your data with minimum error. yeah, so these are the canonical classification, supervised learning problem, classification and regression. So yeah, I can come up with this question that I have encountered recently in practice. So we had a customer in a company that I worked for um, that wanted an age estimation model, and they are actually not doing it right, and they had poor results, and they came to us and asked what is the problem. What they didn't understood that they didn't use the right formulation for the task. So this is also a question for you to answer, which one of these canonical problems will be more suitable for age estimation. Is it classification or regression? So I'm not looking just for the answer, classification or regression, but also for a motivation. Why do you think it's better to model it as a classification problem, or why do you think it's better to model it as a regression problem? So which one and why? Yeah, so also see a question. Yeah, so the non-face images can contain also images that are close to a face, and also random images, yeah, in order to make sure that you do not have false positives around the face. So this is an answer to Tudor. Sorry for the late answer. Okay, so yeah, we have an answer, regression, because the age is a continuous variable. It could be an accepted answer. Yeah, we have some useful answers here. So yeah, I'm going to present. So the main idea is that in regression, you have continuous values. So the age is a continuous variable. But why is this important? So for example, when you try to learn a model, so let's say in classification, for example, you measure the accuracy using right or wrong. So for example, even if you have some age groups, or if you try to actually identify the precise age in years, well, if you don't get the precise answer correct, so for example, my model, let's say my actual age is 33 and the model predicts 35, okay? So in the case of classification, the model is wrong, and this will be an error. So it will have no indication that it was almost right. While in regression, actually, this prediction is better. It's better to say 35, let's say, than 70 or 10 years. So if you have a larger error in regression, you will penalize the model accordingly. While in classification, if you do not predict the exact age, you get an error, but you get equal a penalty if it's 35 or 70. So yeah, in this case, it is better to model this problem with regression. Okay, so going on, yeah, the supervised learning paradigm essentially has this function f that we want to estimate from the data points x and y. So the red, the highlighted red things are important. So you do this through a learning process by building some function f hat, where you want to make sure that f hat produces the corresponding label for your input. So this is the learning part, and what we actually do in practice is once we learned our model on some training data, we then want to put the model to estimate or to predict the output for new data for which we do not know the labels. So in the end, the model is evaluated on different data in order to make sure that it has good predictions. So we will also cover this aspect in a future slide. So actually we will discuss about naive Bayes in the next lecture, and also about performance metrics, k-nearest neighbors, decision trees, and random forest, support vector machines and kernel methods in lectures 5 and 6, and neural networks in lectures 7, 8, and 9. So next we discuss about unsupervised learning. So we have an unlabeled training set of examples. So in this case, we can only try to group the examples based on some sort of similarity. And here the task is more difficult because the similarity can be expressed in different ways. So for example, if you think about images, if you want to cluster them according to the object classes, well, this might be your goal, but in the end you might end up clustering images based on different kind of similarities. So in this case, for example, these two images can be put together based on the pose. So there is some dog with hand like this and a monkey with a hand in the same position. So this is one type of similarity that you might not be aware that is present in your data, and you might end up with groups that are not necessarily do not necessarily represent what you want. So here the problem is it's a bit more difficult to model. But with images that are can be modeled in an easier fashion. For example, for the MNIST dataset, you can apply clustering successfully. So there are not so many ways in which you can cluster images of digits. So here you get a really representative clustering, and the accuracy can be as high as 80 or 90%. Okay, so this is one task in unsupervised learning. Another one would be unsupervised feature learning. So we will discuss this in more detail in the deep learning lecture, because it usually involves deep models. Yeah, this is also considered unsupervised learning. So here you do not have any labels for the data. So what you do, you take your input, you add some noise on top of it, and then you design some neural network architecture that has a bottleneck layer. So this representation is squeezed into some vector of erla n, where n is much smaller than the size of the image. And then from this representation, you want to decode it back into the image, but without the noise. So while you learn to remove noise from this image, you will also learn an effective representation of this image. So once you have this representation, you can apply, for example, some supervised model on top of it. So this kind of approach is very useful when you don't know how to extract features from images or from, I don't know, data that you are not expert on the respective domain. Okay, so one application of this idea, so it can also be used to to learn this representation, and this type of representation can also be used in application domains like abnormal event detection, and this was proposed in a recent work from our group, where we train these autoencoders on top of objects extracted from video frames, and we learn some useful representations to learn for normal objects, and then we assume that for abnormal objects or abnormal events, the representation will be different. So yeah, it's an interesting application, and another category of tasks that falls also in unsupervised learning is clustering using hierarchies. So instead of using a flat clustering like a partitioning, we have a hierarchy of clusters. And the typical approach here is in DNA analysis, where mammals and animals can be organized into this hierarchy. So this is one application. Other applications are in NLP, where you can also organize, for example, novels in the same architecture. So and you will there are these nice these nice dendrograms where you see that for example, novels are separated by genre, like I don't know, different types of literature or books about technology and so on, and then they are separated by time at a different level in the hierarchy, like the time period that they were written, and then they are separated by the style of the author and the type of writing, like romantic or realistic and so on. So you find these interesting patterns in the data that you can extract into a hierarchical model. So yeah, in the end we have two canonical forms of unsupervised learning: clustering, which covers both partitioning and hierarchical clustering, and dimensionality reduction, which refers to projecting the data from a higher dimensional space. In this case, we have a projection from a 2D space to a one-dimensional manifold. So yeah, using autoencoders, you can learn this type of a nonlinear manifold, but we will also discuss about principal component analysis, which makes a linear projection of the data points. Yeah, so regarding clustering algorithms, we will discuss about k-means and dbScan. For hierarchical clustering, we will also introduce this algorithm with different types of ways to build the trees, the hierarchical structure. And for dimensionality reduction, we will discuss about principal component analysis, and also t-SNE, t-distributed stochastic neighbor embedding, is an approach to build data visualizations, but it's mainly an approach to do dimensionality reduction. It's only that the number of dimensions are very, very small when you do it, and it's more suitable for data visualization than for extracting useful data representations. It's also specific to the data that you apply on, and it's not really generalizable as other dimensionality reduction methods. So yeah, it's used only mainly for visualization. Okay, and yeah, there are many other models, of course, that are not covered. So we're trying to cover most of the model in these lectures. And yeah, there maybe I'll go skip through some of the slides with other learning paradigms that I'm not going to discuss and are also not the subject of this lecture. So we can also have semi-supervised learning, in which we have some examples with labels and some examples without labels. We also have reinforcement learning. So these paradigms are somewhere between supervised and unsupervised. So in semi-supervised, you have examples with labels and without labels. In the reinforcement learning, you have labels, but they are not given for every example, and the examples have a temporal order. So the system here tries to learn some intelligent behavior with some reward signal after it takes several actions. So this is more suitable for example, for learning to play Go. This is one success story from Google, where they built the AlphaGo system. Previously, it was thought that it is impossible for computers to learn to play Go. And actually, they proved that they can beat the world champions this game, and they mainly used this learning paradigm called reinforcement learning. Yeah, so it's very hard to train because you get the reward if you win or lose the game, and the board has many configurations, and you take a lot of actions until you get your reward at the end. So it's very hard to train. You need to train for a lot of time and weeks until you get results. Other examples are, for example, teaching a robot to ride. So reward is for moving forward, or negative reward for falling. Other examples are systems that learn to play video games from images. So this is what slightly more related to what people do. So people, when we play a video game, we see the screen and we react to what's happening on the screen. So people try to do the same with Atari games, and they were successfully at this task with reinforcement learning. So once again, here you have different actions, like you move your board on the screen up and down, and then you either win, so the ball gets past the opponent, or you lose if it gets past you, and so on. So this is reinforcement learning. It is usually formalized with graphs that can be optimized with dynamic programming for very small problems, or approximation for larger graphs. And here we need learning. Okay, so also the and what's interesting, in reinforcement learning, that since the supervision comes only at the end, the system can make many different actions along the learning process. So when they built AlphaGo, actually the contestants and also the narrators were really surprised by the moves. So actually they learned new strategies from AlphaGo that previously seemed unreasonable. So it was really interesting to see this. Okay, so another formulation is active learning. So here the problem is also kind of similar to semi-supervised learning, only that so you have a unlabeled pool of images, and you're thinking about choosing the right examples to provide to annotators to label. So you cannot give them the entire pool, because it will take too much time for them. So, and also perhaps if the annotator is for example an expert, like a doctor in medicine, it will be probably expensive, and he will not have the time to annotate thousands of images. So then you have to choose some examples for him to annotate. You give him a small batch. You try to train your model and figure out where the model is not so robust, in what areas, and then you try to choose new examples and so on. So this whole process is called active learning. Then we also have transfer learning, where we train a model for some specific task, and then we take some part of the model. So for example, this is more common with neural networks. So we know that, for example, networks extract features that are generic to different images, even if they solve a specific task. So in the first layers, they learn to extract edges and corners and so on. Then they build up these features into more complex patterns, like textures or motifs and so on, and then they go to object parts and complete objects. So if you take some of these features, so we take the part of this network and try to apply it on a different task, in which you don't have so many training images, you will probably get good results. Yeah, and this is one example in which our group obtained state-of-the-art results in facial expression recognition on 2 data sets using this type of learning. So we used here 3 models, 3 deep learning models. One is trained on pre-trained on face recognition. So we adapted the model for facial expression recognition. So we used the pre-trained part and fine-tune the model on our task. And we also use the model that is pre-trained on ImageNet, the VGGF, and we also trained a model from scratch. So using the idea of transfer learning, you can improve your accuracy. So another example of transfer learning is particularly zero-shot learning, in which you have some images of classes with labels. So let's say we have images of sheep, foxes, and so on. And in the end, you want to train a model that will also be able to classify target images showing different object classes. So here you have sheep and foxes and other classes that are disjoint from this set of classes. So in the end, zero-shot learning means that on the target images, you will not see an image of a bear during training time. So this is an interesting learning paradigm that's also somewhere in between unsupervised learning and supervised learning. Yeah, so there are many interesting applications. I try to cover most of them, and there is also one important question that I want to raise the awareness around. This is the ethical aspect of AI. So yeah, there is this question: what is ethical and what is not? So when it is okay to apply machine learning and AI to solve a problem, and when it is not. So I think this is really important, because in many cases there is no solution, because this is also an ethical paradox even for humans. So perhaps you previously heard about the trolley paradox. So essentially it is posed as a trolley that comes down some train tracks, and it can kill 10 people, and you are a person that has a lever that can shift the direction to kill only one person. So the question is, do you intervene or not? So of course, if you intervene, you will kill only one person, but if you let things happen, the train will kill these 5 people. So yeah, there are different ethical viewpoints here. For example, there is the utilitarian viewpoint that states you should make the choice with the minimum cost. So in this case, you'll have to intervene. But this is not always applied in life by humans, and it is also impossible to apply, because the paradox is actually a paradox. So it's not it doesn't have a solution. So one counterexample here would be, for example, a doctor that has 5 patients that require organ transplants, and one day he receives a new patient that is made some investigations, and he's perfectly fine. But the doctor sees that, according to the investigations, that his organs fit for the 5 people that are about to die. And you can you can recognize that it's the same paradox and pose the same question. Should the doctor kill this perfectly healthy patient just to save the lives of the other 5? Is it ethical or not? So, of course, in medicine, doctors do not kill their patient to save other lives. But it's still the same paradox, showing that there is no solution. And also to raise the awareness, there is this link. So this is also linked, for example, to autonomous driving. So for example, a car that's autonomous and it's based on an AI system might be put in this kind of situation. So do I go forward and kill this person, or do I turn the vehicle and perhaps kill these other people, and so on? So actually you can try to play with this called moral machine, and so you act as the self-driving car, and you think what it should do. So you choose one option or the other, and by the end you will see the results. So you actually look here really about the aspects. So here there is a small girl that's passing on green, and here there is an old lady passing on red. So there are different aspects that you can consider. Here you have a driver, so if you this person is passing on red, so it's really about are these people following the rules? So are they passing always on green, or are they young, or are they women, or are they pregnant, or are there thieves? So there are different aspects that are trying to model in this moral machine. Okay, so you have the link here, you can play with it. We also have I also prepared a reference list of books that I think are interesting and you should read, and some of the slides and the presentation are based on these books. Okay, so okay, so you can write an email if you have any questions. Let me go back to live stream and see if there are any questions here. Okay, so okay, so people make a lot of jokes, I see here, but yeah, I don't see any serious questions. Okay, so guys, thank you for participating. See you next week at the same time.